Hello and welcome to this film, which is all about average bond enthalpies. It's the third in a series of films about the standard level energetics topic, and I'm kind of assuming by now that you're comfortable with the terms endothermic and exothermic changes and that you know what kind of processes involve these changes. Hopefully by the end of this film you'll also understand the meaning of something called the average bond enthalpy and the activation energy, and you'll see how these two things are related to one another. What's more, you'll be able to use average bond enthalpies to calculate enthalpy changes for chemical reactions. And what I might do first of all is to think about picturing chemical reactions in sort of general terms. Okay, now here's an energy level diagram for a chemical reaction. What do we already know about energy level diagrams? Well, if the reactants are higher in enthalpy than our products, then the enthalpy change, which we ought to be able to mark on an energy level diagram as being the difference in enthalpy between our reactants and products, the enthalpy change is here, and it's got to be negative for this particular process. But what we can also see on this energy level diagram is that there's something else marked along the way. It's like a hill that the reactants have to get over before they can get to the product. And I suppose you might wonder why, if you've got reactants that are less stable than your products, why they don't automatically just turn into those products in all cases. Well, here, if we try and picture what's going on in a chemical reaction, we might decide that this collection of atoms over here can be turned into this collection of atoms over here, but only if we break up the bonds in the reactants first, turn them into separate atoms, which can then be recombined in a different way to form the products. But in doing that, we have to make new bonds. Now, breaking bonds is always endothermic, we know that. Making bonds is always exothermic, right? This EA, the activation energy for a reaction, refers to the fact that you're never going to get over this hill unless you put some energy in first to break these bonds. So the activation energy can be described as the minimum amount of energy that we need to supply in order to allow our reactants to take part in a reaction. What else can we see from this energy level diagram? Well, hopefully we can see that the difference in energy between these two quantities is going to provide us with this quantity. All right, so our enthalpy change can be calculated so long as we know the amount of energy that was used in breaking the bonds and in making the new ones. But unless we know how much energy each bond has, we can't calculate this. But if we do, if we can look these things up, then it gives us an easy way of calculating the enthalpy change. When we look these things up, what we're looking up is things called average bond enthalpies. But not only do we have to be able to look them up in an IB exam, we also have to be able to define what they are. So this is a really important definition to learn. The average bond enthalpy is the enthalpy change when 1 mole of a particular type of bond is broken. So, for example, I could be talking about a carbon-hydrogen bond. But it's important to realise that the carbon-hydrogen bond can have a different amount of energy or require a different amount of energy to break depending on what kind of context it's in. So in other words, in one molecule it might require X amount of kilojoules per mole. In another molecule it might require Y kilojoules per mole. Okay? So to take into account this fact, what we've done is we've averaged the amount of energy required to break this kind of bond across a huge number of different molecules that contain that bond. So that forms quite an important part of our definition. Okay? The average bond enthalpy is the enthalpy change not only when 1 mole of a particular type of bond is broken, but this is averaged across various molecules containing that bond. So now, if we look at a particular chemical reaction, so a specific one here of burning methane, right? Burning is an exothermic process, we know that, right? So we ought to be expecting to see a negative enthalpy change, and indeed that is what we've got here. We've got a negative delta H, okay? So if we bear in mind what's going on in this reaction, we've got our reactants over here and our products over there. What we can say, remember, is to get across this hill, we've got to break up the bonds in our reactants. So we've got to break up all the bonds in the CH4 and the 2O2. We'll now end up with separate atoms. We'll be at the top of the hill. Okay? Once we've done that, we can then make new bonds, and we'll be making the bonds in our products here. We'll be starting from the separate atoms. We'll be heading downhill because making bonds is always exothermic, right? Whereas the breaking was endothermic. We can calculate what the enthalpy change, sorry, not what the enthalpy change was, what the activation energy was for this process by figuring out how much energy we had to put in to break all the bonds. But what we're doing here is calculating the enthalpy change. So let's not worry about that too much for now. Okay, and let's look at what we do when we put all of this together. Right, so we've got to break the bonds in our reactants. We've got to make the bonds in our products. Remember, to get over this hill, we've got to end up with separate atoms over here. We're going to have an activation energy there, but what we're doing here is we're trying to calculate the enthalpy change. So that's this quantity here. Remember, that is the difference between these two values, and the difference is simply a subtraction. So if we subtract the energy released by making the new bonds from the energy required to break the old bonds, then we will find the enthalpy change. And here is a really important formula to remember. Now, if you can't remember it, then hopefully you can figure it out from an enthalpy level diagram. Okay, but we can calculate the enthalpy change for any process by adding up all the bonds broken and subtracting the bonds made, which seems simple enough, particularly if we're given bond enthalpies in a table. Right? There is just one last place that we might fall down here though, and that's if we can't figure out what bonds there are in the reactants and products. And if you can't draw electron dot diagrams for covalent molecules, then that might be a problem for you because you might not be able to figure out what bonds there are. But anyway, assuming that we can figure out what bonds are broken and what bonds are made. Okay, we've got 4 carbon-hydrogen bonds here, so 4 times 4, 1, 3. We've got 2 oxygen-oxygen double bonds. These are not oxygen-oxygen single bonds, so if we use that one, we'd be wrong. Okay, we need 2 times 4, 9, 5. If I add that lot up, hopefully I've done it right, I get 2, 6, 4, 2. Okay, what bonds are we making? Well, we've got 4 oxygen-hydrogen bonds in 2 water molecules. So I've got 4 times 4, 6, 3. As I say, if you can't draw these, if you can't picture them in your mind, then you may well get the number of bonds wrong. In particular, with molecules like carbon dioxide, where you need to know that this is a carbon-oxygen double bond and that there's 2 of them. So 2 times 799 from the table. Okay, and if I add that lot up, I get 3450. And the last thing for me to do is to take this 3450 from the 2642. So 3450 minus 2642 equals minus 808 kilojoules per mole. Why kilojoules per mole? Well, because that's what it says in the table here. These are all given in kilojoules per mole. And what you might also notice is that they're all positive values because we're breaking bonds, right? Why is this one a negative value? And this is worth checking at the end because we expected this to be an exothermic change because we're burning methane. Okay, so that's always worth checking at the end of one of these calculations. Have you got the sign right? Now, there's just one more thing to mention in this film, and that is the difference between a calculated value, which we just found, remember, for this reaction we decided it was minus 808 kilojoules per mole, and an experimental value, which it turns out is minus 890 kilojoules per mole, which means that when someone actually did this reaction, they measured the heat change or the enthalpy change, and they decided that for every mole of methane, 890 kilojoules was released. And there's quite a substantial difference between those two numbers. Where could that have come from? Well, remember, when we calculated this value, we used average bond enthalpies. Okay, so these are values for these bonds which aren't the same in all cases. So we ought to expect some discrepancy here, and that's a really common question to see. Why is there a difference between the calculated and the experimental value? And you simply refer to the fact that because we used average bond enthalpies, we're not necessarily using exactly the right amount of energy for each bond. Okay, well, there was quite a lot covered there, but I suppose one of the most important things was that formula there on the screen, and that is that the enthalpy change is the bonds broken minus bonds made. But hopefully in addition to that, you also know how to define average bond enthalpy, you know how the activation, what the activation energy is and how it's related to bond enthalpies, and you can also calculate the enthalpy change using that formula we just saw on the screen. As usual, any questions or comments, please come along and see me or post a comment on YouTube.